In this outcome, we explore magnetic fields and how engineers put them to work. We'll look at the patterns fields make, the forces they produce, and the neat hand rules that connect field, current, and motion. Let's get going. Here's a quick map of where we're heading. We'll start with permanent magnets and the magnetic behavior of iron and steel, then learn to draw and describe field patterns. From there, we'll see how an electric current creates its own magnetic field, meet the force on a current-carrying conductor given by force equals BIL, and use the right-hand and left-hand rules to sort out directions. We'll finish with some real engineering uses of magnets and electromagnets. Let's begin with permanent magnets. These keep their magnetism without any electric current at all. Every magnet has two poles, a north and a south, and the familiar rule applies. Like poles repel, unlike poles attract. One curious fact is that poles always come in pairs. You can never isolate a single north or south pole on its own. The region around the magnet where it exerts a force is its magnetic field, and we measure the flux density, B, in Tesla. Why are some materials magnetic at all? Iron, steel, nickel, and cobalt are described as ferromagnetic, meaning strongly magnetic, and that's down to tiny magnetic regions, inside them called domains. In an unmagnetized sample, these domains point every which way, cancelling out, but apply a magnetizing field and they line up, so the whole sample becomes a magnet. Once every domain is aligned, the material is magnetically saturated, and heating it or applying a strong opposing field can scramble the domains again. We split magnetic materials into soft and hard. A soft material, like pure iron, magnetizes easily in a field but loses its magnetism as soon as the field is removed because its domains realign so readily, which makes it ideal for electromagnet cores and transformers. A hard material, such as steel or special alloys, is harder to magnetize but holds on to its magnetism afterwards, with its domains locked in place, and that's what we use to make permanent magnets. Let's fix some terms. A magnetic field is the region around a magnet or current where a magnetic force acts. A magnetic pole is a region, north or south, where the field is strongest. Ferromagnetic describes a material like iron or steel that's strongly attracted by a magnet. A domain is a tiny region inside the material where the atomic magnets all point the same way. Flux density, B, measures the field strength in Tesla, where 1 Tesla is 1 Weber per square meter. And saturation is the state where every domain is aligned and the material can't be magnetized any further. There are a few simple rules for drawing magnetic field lines. Outside the magnet, the lines run from the North Pole round to the South Pole, and inside the magnet, they run south to north, forming closed loops. Lines never cross one another, and where they crowd close together, the field is strong. Each line carries an arrow showing the field's direction, and that direction is simply the way a North Pole would be pushed if you placed it there. Let's picture the field of a single bar magnet. The lines leave the North Pole and curve gracefully round to the south, and the whole pattern is symmetrical about the magnet's long axis. The lines are packed closest, and the field is strongest right at each pole, while the field is weakest midway along the side of the magnet. You can reveal this pattern for real with a plotting compass or with iron filings, and it's the standard case you may be asked to describe. Now bring two magnets together. With unlike poles facing, a north opposite a south, the lines run straight across the gap, pulling the magnets together. That's attraction. With like poles facing, say north opposite north, the lines push apart and refuse to meet, and a neutral point forms between them where the field cancels to zero. The pattern is a lovely visual explanation of why like poles repel and unlike poles attract, with the lines behaving almost as if they're under tension. Here's the discovery that links electricity and magnetism. Back in 1820, Ørsted noticed that an electric current deflects a nearby compass needle, which showed that every current produces a magnetic field around it. Switch the current off and the field vanishes. Reverse the current and the field reverses too. This intimate link, electromagnetism, is exactly what lets us build electromagnets, motors, and relays. Consider the field around a straight current-carrying wire. It forms concentric circles wrapped around the wire, closest and strongest near the wire, and spreading out and weakening further away. To find which way the field circulates, use the right-hand grip rule. Point your thumb along the current, and your curled fingers show the direction the field goes round. Reverse the current, and the circles reverse too. And a note on symbols: a dot means current coming out of the page, a cross means current going into it. Now bend that wire into a single loop. Doing so concentrates the field inside the loop, with the field lines passing straight through its center. Inside the loop, the circular fields from each part of the wire add together and reinforce one another. The upshot is that one face of the loop behaves as a north pole and the other as a south, so the loop starts to act like a very short bar magnet. Take that idea further and wind many turns into a long coil, and you have a solenoid. Inside it, the field is strong, straight, and very nearly uniform, while outside the pattern looks just like a bar magnet's. To find its poles, use the right-hand grip rule again. Curl your fingers the way the current flows around the turns, and your thumb points to the solenoid's north pole. Slip a soft iron core inside, and you've got a powerful electromagnet. Let's compare a solenoid with a permanent bar magnet. The solenoid, an electromagnet, only has a field while current flows. Its strength depends on the current and the number of turns. Its poles swap over if you reverse the current, and best of all, you can switch it on and off. The permanent bar magnet, by contrast, always has its field, its strength is fixed, its poles are permanent, and you can't simply switch it off. That switchability is the electromagnet's great advantage. Let's pause and check. Could you sketch the field around a bar magnet and mark the direction of the lines? How does the field around a straight wire differ from the field inside a solenoid? And which way do the field lines point outside a magnet, north to south or south to north? Have a think before we carry on. Here's a central idea, the motor effect. A wire carrying a current in a magnetic field feels a force, and that's the basis of every electric motor. For a wire at right angles to the field, the force equals the flux density times the current times the length. Force equals BIL, with force in newtons, flux density in Tesla, current in amps, and length in meters. The force is greatest when the wire and field are perpendicular, and it drops to zero when the wire lies along the field direction. To find which way that force points, we use Fleming's left-hand rule, the left hand specifically, for the motor effect. Hold your thumb and first two fingers at right angles. The thumb stands for thrust, the force or motion. The first finger is the field, pointing from north to south, and the second finger is the current, in its conventional direction. Line them up and your thumb reads off the direction of the force, and if you reverse either the current or the field, the force reverses too. Let's calculate a force. A straight wire 0.20 meters long carries 5 amps at right angles to a field of flux density 0.40 Tesla. The force equals BIL, so we substitute 0.40 times 5.0 times equant 20. Working it through, 0.40 times 5 is 2.0, and 2.0 times 20 gives 40, so the force on the wire is 40 newtons. This time we're after the flux density. A conductor half a meter long carries 10 amps perpendicular to a field, and the measured force is 1.5 newtons. Start from force equals BIL and rearrange for B, so B equals the force divided by the current times the length. Substitute 1.5 divided by the quantity 10 times 0.50. The bottom is 10 times 0.50, which is 5.0, so B equals 1.5 over 5.0, giving 0.30 Tesla. Now a coil with several turns. It has 50 turns, each about 10 meters long in the field, carrying 2.0 amps in a field of 0.50 Tesla. For n turns, the force becomes B times I times N times L. Substituting, that's 0.50 times 2.0 times 50 times 0.10. Step by step, 0.50 times 2.0 is 1.0, times 50 is 50, times 0.10 gives 5 mole. So the total force is 5.0 newtons, much larger than a single turn would give. Let's find a direction using the left-hand rule. A wire carries current from left to right, and the magnetic field points into the page. Set your first finger, the field, pointing into the page, and your second finger, the current, pointing to the right. Hold them at right angles on your left hand, and your thumb, the force, points straight up the page. So the force on the wire is directed vertically upwards. Let's collect the key terms. The motor effect is the force produced on a current-carrying wire in a magnetic field. A solenoid is a long coil that produces a bar magnet-style field when it carries current. An electromagnet is a solenoid with a soft iron core, giving a strong, switchable field. Fleming's left-hand rule links the directions of force, field, and current. The right-hand grip rule gives the field direction around a wire or solenoid. And the Tesla is the SI unit of flux density, where 1 Tesla gives 1 Newton per amp per meter. How do we make a magnetic field stronger? More turns on the coil gives a stronger field, and so does a larger current. Adding a soft iron core dramatically boosts a solenoid's field. And we choose soft iron specifically so that the field switches off cleanly when the current stops. These few levers let engineers design a magnet to hit a required strength. And remember, the force on a conductor rises in step with the flux density. Let's see where all this shows up. Electric motors use the motor effect to turn coils and drive machinery. Loudspeakers move a cone with a varying current in a coil to create sound. Relays let a small current safely switch a much larger one. Scrapyard cranes use switchable electromagnets to lift and drop steel. Generators, transformers, and maglev trains all rely on magnetic fields too, while permanent magnets quietly do their work in compasses, fridge seals, sensors, and holding catches. Time for a check. Can you state the formula for the force on a current-carrying conductor and name each term? If a wire carries current upward in a field pointing to the right, which way is the force? And can you name 2 ways to increase the force on a conductor in a magnetic field? Give those a try. Let's draw the threads together. Both magnets and currents create fields with recognizable patterns. Iron and steel behave as magnets because their domains line up. Every current produces a field, and a solenoid neatly mimics a bar magnet. A current sitting in a field feels a force given by force equals BIL, with the left-hand rule finding the force direction and the right-hand rules finding the field direction. Together, these ideas underpin motors, loudspeakers, relays, and generators.
Let's check your understanding. How does a diode turn AC into DC? Can you define the period and frequency of an AC supply and state the link between them? Can you explain how the earth wire and fuse work together to keep an appliance safe? And can you state 2 hazards associated with mains electricity?